Apparently I'm being recorded. Okay, good. Which was poisoned by industrial mercury dumping in the 1960s and 70s. And it's been reported that people in this First Nation community show quite a lot higher than normal incidence of birth defects. But the individuals concerned show normal mercury levels. So this is not mercury that's in their bodies. It's mercury that the previous generations were exposed to that may be causing this. Anyway, mercury DNA damage is similar to that caused by ionizing radiation. So you get things like single strand breaks in DNA. But unlike radiation damage, mercury-induced damage is not readily repaired. And moreover, mercury inhibits the repair of radiation-induced damage. So it's an interesting phenomenon. Now, where we started this whole business is mercury is known to bind thymine bases, which is a component of DNA. Here's my primer on mercury, on DNA structure and possible places mercury might bind. This is a cartoon of the familiar structure of DNA, and you all probably know it. It's characterized by A, T, and GC base pairs in the double helix. And what's thought to occur is mercury is thought to be bound by cross-adjacent thymines. So here's a place in the middle of this DNA strand here, where there's A on either side and T on either side, and it binds across the two thymidines or thymines. This is a cartoon of the thymine and adenine, and you can see thymine has this pyrimidine base with a nitrogen, an NH here, and two carbonyls on either side of it, and we'll come back to that in a minute. So we thought we would have a look at this and see how it bound. And we began computationally by computing, just doing geometry optimizations using density functional theory and using this as a model for mercury 2 binding to thymine. And there are lots of ways it can bind. There are these oxygen groups here and the nitrogen groups also. And I have to point out there is prior art here that people have looked at the structures of mercury bound to DNA, very often using biochemically relevant base sequences along the length of the DNA, and they see unusual ways in which mercury binds to all kinds of DNA bases. Anyway, the simplest way that mercury might bind is by binding the N3 nitrogen of the thymidine here, and you could calculate the geometry of it restricted in this sort of planar. This is the syn periplanar geometry where the nitrogens are on the same side. This would be the geometry that you would find in DNA. And this is the synclinal geometry where there's a torsion angle from around the mercury nitrogen axis, where this is these rings of these planes are at 90 degrees. These planes, the planes of these rings are at 90 degrees to one another. Then there's the anti-periplanar geometry where you're again bound by the N3 nitrogens. This is the lowest energy, but it's not lower than by very much, only 11 kilojoules per mole. This is the next one up above the syn periplanar, very close in energy to this, only 0.9 kilojoules per mole above this particular one. And here the nitrogens are on the opposite side. This couldn't form in DNA. And then there's the various combinations with oxygen binding here, which are higher in energy and would be considered unfavorable. And finally, the least favorable, where it's bound to two oxygens. And if anyone wants to know the details of how we actually got the mercury to stick to these various locations, I'm happy to share them. Needless to say, if you start off like this and do a geometry optimization, you end up like this. If you don't use any constraints or restraints to hold the mercury glued to the oxygens here. So we can do things like with DFT, like look at the dependence of this torsion angle here, the energy versus torsion angle. And the bottom line here is there isn't a big penalty twisting this around this torsion angle phi here. So you could probably, the coplanar orientations are not prohibited, you can conclude from the DFT. The next thing we thought we would do is we would look at 1-methylthymidine, which is our model for the thymine in DNA, and we would solve the crystal structure of this. There was an old crystal structure published a long time ago with an R of about 7% or something. So we decided we were going to do the same. We're going to repeat this, and we reevaluated it at about 1.2% R, I think. And that allowed us to see the hydrogens in the crystal structure. And basically, it confirmed the previous structure, but we got a little bit better bond lengths and things like that out of it. And confirms the NN3' binding of Mercury 2 and the anti-periplanar conformation preferred due to crystal packing forces. And you can see there's a sort of analogous base pair stacking going on in the crystal structure, which is kind of a nice thing. We also looked at solids versus solutions. In the solution, we would expect this synclinal, where the rings are oriented at 90 degrees to each other, geometry to be the predominant one. What I'm not telling you is that there are some oxygens above and below, and probably waters on either side of this as well. Basically, the X-AFs are quantitatively consistent with both crystallography and the calculations, both for the solution species here and for the crystalline solid. Now I want to talk a little bit about HERF results. HERF is a very cute technique that's available at SSRL. They have used to be based on beamline 6.2, but recently been commissioned is the beamline 15.2, and all of that has been moved over there. HERF gives you a chance to overcome the core hole lifetime broadening of the primary photoexcitation event in X-ray absorption spectroscopy. So here's XAS here in blue. This is dimethyl mercury. And what we're doing is we're measuring the X-ray fluorescence with a resolution that's much greater than the natural line width. And we're just measuring a narrow band, in this case of the mercury LL41 peak, and we're following that and plotting the fluorescence, the excitation spectrum effectively, and that's the HERF. It stands for high energy resolution fluorescence detection, XAS, X-ray absorption spectroscopy. Some people call it high resolution XAS or high resolution Zanes. I personally don't like that nomenclature because it's not quite the same thing. It would be if all of the transitions are on the diagonal of what's called the Rix plane, but very often you get things that are off diagonal, in which case as your HERF is measured along diagonals in the Rix plane, you are selecting from amongst a bunch of possible XAS transitions. So rigorously speaking, you should not call it HRXAS or HR Zanes, but rather HERF is fine, I think, because it sort of it makes it seem different, which it is. Anyway, so the bottom line here is you get this beautifully exquisite increase in resolution, and you get really lovely spectra. This shows a comparison of the mercury bisthymidine complex in solid, in solution, with some sort of biological relevant type complexes. Mercury likes to form coordination compounds with thiolate donors, and here's two cysteines bound to mercury, and here's the spectrum. It also likes 4 coordinate species, and our prototypical example is DMPS, which is dimercaptopropane sulfonic acid, which binds via a single sulfur to form a 4 coordinate species that looks rather like this. And you can see they're very characteristic HERF spectra. The regular, as some people call it, or near edge spectra, as I prefer to call it, they don't show nearly as much variability, although it is possible to distinguish these by just looking at the near edge alone. But the HERF makes it very plain that, in fact, these types of compounds have a very unique looking spectrum with a very intense pre-peak and characteristic double peak past the edge and a broad hump at around 12325 EV, or just below 12325, about 12324 EV. And so these have a very characteristic fingerprint-like spectrum that perhaps could be useful in looking at biological samples or cells or even tissues, or even various other things. We did some ORCA DFT ROSIS simulations. At the time we did these, the TD-DFT with spin-ORIC coupling wasn't available. I believe it now is, although we haven't really played with it extensively yet. And basically, we only included the first 150 transitions. We naively tried to go much higher than this and ended up running out of memory in the machine that we ran it on, and writing more than a terabyte of files. I think it wrote to a 2 terabyte disk and it filled it. So we went to several hundred transitions, hoping to be able to duplicate the doublet structure up above 1, 2, 300 EV, but unfortunately we had to stop at 150 transitions. Nonetheless, these showed that with phi equals 0 and phi equals 90, we would expect similar spectra, which is in full agreement with what we observe. Now I want to change gears a little bit and think about DNA itself. So we've looked at the spectroscopy of a model system, and now I'd like to think about DFT modeling of Mercury 2 binding. The first thing we tried was a DFT calculation on a small piece of DNA. Now, DFT is notoriously poor at modeling weak intermolecular interactions, things like dispersion, things like the pi-pi stacking of base pairs in DNA. And if you use an ordinary functional in DNA to do in DFT to do this kind of calculation, you'll find that it'll just fly apart. DNA won't hold its tertiary structure. However, modern approaches, including the so-called meta-GGA M11L functional, are designed to take account of some of these intermolecular forces, not really intermolecular in this particular case, but so we started with this, and we ended up doing a calculation of a small segment of DNA, 4 base pairs, and we were delighted with how well it reproduced the crystal structure. So here's a crystal structure containing an AATT sequence right in the middle of it, and you can see that the green is the DFT and the pink is the crystal structure, and superimposing the two, there is really a little bit of difference. The backbone is predicted to be a little bit bigger with the DFT, particularly at the ends, which perhaps isn't surprising because this is only a 4 base pair stretch of DNA. I would have liked to have done more, but this has got more than 240 atoms in it, which is perhaps a reasonable limit for most DFT geometry optimizations. Anyway, we put in Mercury in this stretch of DNA, and basically, no matter where we started it, it always ended up between the central 2 thymidines, which is a nice thing that to have found. Basically, we started off bound up here, and it would migrate back down to the central ones, and it binds just as people thought it would, cross diagonally across, displacing the thymidine from its position associated with this adenine here, and this thymidine associated with this adenine here, causing a bridge between the DNA. But the overall structure of the DNA wasn't particularly perturbed. So if you look at the outside of the DNA double helix, it wasn't particularly perturbed from its original conformation. So Mercury can just slot in the middle. It can twist the innards a little bit, and it's going to hold it together. It's going to interfere with things, but it's not going to change the outside very much. So we also thought we should try a longer piece of DNA, and we decided that really the DFT of a long piece of DNA probably would be impractical. So we explored MMQM approaches. That's a combination of molecular mechanics and quantum mechanics. And we first did a pure molecular mechanics geometry optimization of this exact piece of DNA from the crystal structure that we'd chosen to start with, which was the highest resolution one that we could find, which had this AT region in the middle. The pink shows the crystal structure, just as it did in the last slide. and the green shows the molecular mechanics geometry optimized structure. We used a program called GULP to do this, which incorporates a program that used to be called Cluster these days. GULP used to be just for extended periodic solids, but now it can also do discrete entities such as a little piece of DNA like this. And the two structures really agree very well. And interestingly, the backbone is also predicted in the calculated structure to be larger than suggested by the crystallography. Anyway, the MMQM approach is you would take the atoms binding mercury and you would treat them with density functional theory, and the rest of the molecule gets treated with molecular mechanics, which is very fast and can do things really quickly. And so you have you've turned something that was intractable to something that was highly tractable. And this is what we find. It's basically the same sort of structure. Again, here the green is the unperturbed DNA calculated molecular mechanics geometry optimized structure. And in the middle here you have the DNA thymines bound with the mercury. Here we can't test different starting locations quite so easily for the mercury, because basically you have to predefine which bits of the molecule you're going to start with as your quantum atoms, and which bits are going to be treated with molecular mechanics. Really, the only way to model mercury is with DFT. I think you can't properly do it, so you can't study whether it's going to move around using.
You have 2 minutes.
Okay, I'm pretty much done. Anyway, this agrees with the DFT structure, so we're very gratified to this. Conclusions and next steps. There's lots of next steps. This is sort of a work in progress. So HERF at XAS really, we think, provides a distinctive fingerprint of thymidine-bound mercury 2. We've looked at maybe 30, 40 different environmental and biologically relevant molecular coordinations of mercury 2, and the thymidine coordinated one is distinctive from all of them. The DNA double helix is not expected to show substantial structural changes on mercury binding, but mercury binding will, of course, block important enzymes such as RNA polymerases, nuclease helicases, and possibly transcription factors. Our next steps would be to examine HERF of DNA with mercury bound, and we've actually done a little bit of that, but I'm not going to show you that today. We're going to examine HERFID and HERFID imaging of mercury-treated tissues and cells. Mercury 2 is thought to bind to guanosine, and we would like to follow up looking at guanosine. We expect the guanosine complexes to be distinct, but we haven't done that yet. There's always room for improvement. We would like to do better calculations. Dynamics of DNA with cross-adjacent thymidines bound to mercury are eminently possible. You could use the DFT to parameterize the force parameters for mercury bound in this way and do a molecular dynamics simulation of DNA and ask questions about whether the propeller motions of the bases are changed and various other bits and pieces that people have worried about with molecular dynamics calculations of DNA. You could also do improved simulations of mercury bound to thymidines. And of course, HERFID imaging at cells. Can we speciate mercury in the nucleus? Can we see this in an actual section from a piece of tissue or something like that? And these are the people that provided money, and this is the only SSRL results are shown here, but we do use the advanced photon source and of course the Canadian light source, which is a 15-minute drive away from where I am now. And thanks to the people who funded it. And this is the research group. Photo is a few years old, but I like this particular one. This is only the ladies or the women in the research. I get in trouble for saying ladies. For some reason, that's not PC these days. But this is, so there's a few men, but mainly it's because it's Sanjukta's baby shower. And some of the men didn't want to come. And thank you for your attention. That's the end of my talk.
Thank you, Graham. So does anybody have any questions that they'd like to ask before we move on to the next speaker? I also think that there are questions in the chat for you.
Oh, I didn't see those yet.
Here, I can read it out. So what are the challenges, if any, of applying HERF minus beam damage and need for measuring in a cryostat? It seems very powerful for a range of environmentally relevant elements.
I can answer that. The main challenge in using this method is getting beam time. The beam time is always at a premium, particularly when it was on this oversubscribed beamline 6.2. So we only ever get little tiny chunks of beam time, a few days, and we never run everything we want to. So the main challenge is getting access to the infrastructure. Now that we have 15.2 commissioned, I'm hoping that we'll have more available time, because of course 6.2 is shared with the transmission X-ray microscope, and with the macro scale imaging, and with the tender advanced spectroscopy, such as the K-beta emission that was done on an in-house facility that was shown previously. But all of those things take away from each other, of course. So that's the main challenge. The other main challenge is that to change elements on this setup takes a lot of time, because there's an array of 7 analyzer crystals that intercept a reasonable but still very small solid angle of the total 4 pi steradians of fluorescence coming off the sample. And you need individual element-specific analyzers. So, for instance, Mercury uses a 555, a silicon 555 reflection. If you want to do another element, then I think, for instance, zinc, you need a silicon 642 analyzer. You need a different crystal. So you have to swap all those out, or the beamline scientists will swap all those out and spend a long time changing things over. So practically, it's one run per element. You don't mix and match like you do with XAS. You can't go to the zinc edge and quickly look at the zinc.
Great, thank you for that. A very thorough